We are used to measuring distance in kilometers, tens, thousands, hundreds of thousands. On Earth, that's a pretty familiar number. However, that's only on Earth. We are just a tiny speck in the vast universe, where much greater distances are the norm. Let alone the universe, even in the solar system, we measure distance not in the kilometers we Earthlings are used to, but in astronomical units. One astronomical unit is equivalent to the distance between the Earth and the Sun. If we convert this into kilometers, it is 150 million. For example, Uranus is 3 billion kilometers away from our planet, which is 20 astronomical units. Just imagine these scales. And that's far from the limit. On the scale of the entire universe, even astronomical units seem insignificant. That's why we should use the light year here. 1 light year is equivalent to the distance that light travels in a year, excluding the influence of gravitational fields. For example, Proxima Centauri, the star closest to the solar system, is 4.2 light years away from Earth. That's actually a tiny distance, so what can we call a huge distance? And what are the larger structural formations like Khabarov? First of all, let's talk about giant clusters of galaxies. Scientists William and John Herschel were the ones who determined that such structures exist. And they are much larger than other isolated concentrations of galaxies. An important point was that the distribution of such structures in cosmic space was not uniform. In some regions, their concentration was high, while in others it was extremely low. It happened in the 18th century, but 2 centuries later, scientists had much greater opportunities to understand exactly how galaxy clusters are distributed in space. Thus, we found out that a single galaxy in the universe that is not part of any cluster is rather an exception. Usually, several galaxies concentrate in one area under the influence of gravitational forces. And the next, even larger level is the so-called superclusters. Their peculiarity is that they can consist not just of a dozen galaxies, but of hundreds or even thousands. In such clusters, there is also a concentration of gases with high temperatures. Over time, it became possible to estimate radial velocities from extragalactic redshifts, which meant a deeper study of superclusters. Scientists were able to determine the distance to galaxies in this way and model how they are arranged. These were 3-dimensional maps that showed space spanning 1 billion light years. In addition, gamma-ray bursts were especially helpful in discovering supernova clusters. This process itself releases a huge amount of energy. Gamma-ray bursts are mostly characteristic of stars with high rotation speeds and those located in more distant regions. A greater number of gamma-ray bursts occur in those galaxies that are characterized by a high level of activity and where the decay of matter happens more intensely. Scientists studied in more detail how galaxies are distributed and how fast they move, which made it possible to determine superclusters cannot be considered an enlarged variation of ordinary galactic clusters. Structurally, superclusters are more filamentous and have a high density. Inside such formations, there are systems of galaxies. This can be compared to foam, which in its structure vaguely resembles the formations of superclusters. There is no specific shape for such structures. They are absolutely diverse. They can take the form of walls, like for example the Great Sloan Wall. More familiar galaxy clusters like the Virgo cluster or superclusters can take the form of a chain, the Markarian chain. As we've already mentioned, the universe is characterized by inhomogeneity. However, that's not the case everywhere. For example, regions with an area of about 300 megaparsecs can be considered homogeneous. There, between clusters of galaxies, matter is virtually absent. The clusters themselves are filamentous, with a density about 10 times lower than the average value for other galaxies. Galactic filaments can also form here. Perhaps one of the most famous examples of a wall is the Great Northern Wall. Another name is the CFA2 Great Wall. It is the largest after the Great Wall of Hercules, Corona Borealis, and the Great Sloan Wall. The average distance reaches about 200 million light years. The thickness of the Great Northern Wall is 15 million light years. The length of the structure reaches about 500 million light years. These are enormous dimensions, but even this is nowhere near the universe's limit. For example, the already mentioned Hercules Corona Borealis Great Wall is as large as 10 billion light years. And by the way, that's 1/10 of the diameter of the observable part of the cosmos. Let's also talk about the galactic wall that is closest to the solar system. It is located near the constellations of Telescopium, Indus, Pavo, Centaurus, as well as the southern constellation Hydra. The galaxies that make up this wall are at least 25 million light years away from our planetary system. This galactic wall includes galaxy clusters that are also related to the Milky Way. On large scales, over hundreds of millions of light years, we perceive the universe as a homogeneous structure, where all the components are distributed more or less evenly. However, it's important to remember that if we look at a smaller region, we'll find that the components there are distributed unevenly. We need to know this in order to correctly develop a theory of how the universe has evolved. Scientists have developed a three-dimensional model of how galactic structures are distributed in the universe. This helped reveal that on all sides, within a range of 1 billion light years, there are actually clear structures. This means that the distribution of matter in a particular region of the universe, spanning a couple of 100 billion light years, will be uniform. That's why we consider the universe as a whole to be homogeneous. Galaxy clusters are the largest structures in the universe, surpassing even galactic filaments, fibers, and galactic walls in size. The process of formation and development of galaxy clusters has its own characteristics. Such structures expand under the influence of the expansion of the universe. Gravitational forces, on the other hand, can slow this process down. For a galaxy cluster, a galaxy is not only characterized by gravitational lensing. This effect occurs when a light source appears distorted as its rays pass through another structure.
Если лучи от него проходят.
It indicates a large amount of hidden mass from us, which most likely comes from dark matter. It is precisely thanks to it that galaxy clusters form, since dark matter contributes to the attraction to galaxies. In general, dark matter is quite a mysterious structure for us in the universe. We still don't know a lot about its properties. However, scientists have found that dark matter is one of the key factors in the formation of galaxy clusters. It increases the power of gravity. The main question remains in all of this: why is the universe uneven on smaller scales? And here, gravitational forces also play a key role. Structures that are evenly distributed simply accumulate in certain areas under their influence, forming denser regions. The dense process of matter distribution in the universe began sometime after the Big Bang. The increase in the mass of the universe itself contributed to the fact that the rate of expansion began to decrease. In some regions, the expansion not only stopped, but also turned into the reverse process, contraction. This made the unevenness even worse. New clusters of galaxies and voids between galactic filaments were forming. The theory of how galaxies form in the universe in the modern world is called the hierarchical theory. According to this theory, in the early stages of formation, there are individual galaxies that later become part of galaxy clusters. These clusters eventually transform into superclusters. Thus, at the final stages of the universe's evolution, the largest galaxies appear. The thing is, that very homogeneity is characteristic of regions about 300 million light years across. Based on this, it follows that matter in larger structures is distributed uniformly. However, those same galactic walls themselves are not uniform. For example, the Hercules Northern Crown Wall, and it's actually much larger than 300 million light years across. Here we encounter contradictions with the cosmological principle itself. As you can see, the universe's development isn't always obvious to us. Let this be an incentive for us to delve deeper and deeper into the mysteries of the cosmos. This way, we will be able to understand what our universe really is and what place is reserved for us in it. Extinct volcanoes, canyons, changing seasons, a thin layer of atmosphere, all of this sounds very intriguing. Research on Mars is still ongoing. Humanity wants to lift the veil of mystery from the fourth planet of the solar system. There are currently 8 spacecraft in orbit around Mars, and special rovers, or in other words, Mars rovers, are collecting data directly on the surface. These include Curiosity and Perseverance, which have been operating since 2012 and 2021, respectively. There is also a spacecraft called InSight, which began its mission in 2018. Thanks to the data we've received from the spacecraft on the surface and in orbit, we now know a bit more about the past of Mars. For example, that Mars had milder conditions and higher humidity in the past. What kinds of landscapes could we have observed on Mars in the past, and what is happening there now? That's what the research probes will tell us about. We'll start with the Mars Odyssey orbiter. It began its mission back in 2001 and is still active today. During this time, Odyssey has completed more than 94,000 orbits around Mars. Thanks to this spacecraft, we know what landforms exist on the surface, as well as the presence of mineral rocks there. What became especially interesting for us was the fact that there are areas with ice on Mars, but they are located in a part of the planet where this would generally be considered unlikely. Mars Odyssey continues its work, and we will surely receive a lot more new data from it. And this is the Mars Reconnaissance Orbiter, or MRO for short. One of its main tasks is to study the surface, while also searching for areas of the planet where it would be convenient to land a research probe. For this reason, we have many interesting images taken by the MRO's camera. The most remarkable of them is a photo of sand dunes. You may notice that a crust has formed on the surface, and as you remember, we mentioned earlier that Mars has changing seasons. When winter comes to the planet, many changes occur on the surface. Of course, there are no blizzards raging on Mars, and there are no endless snowfalls, even though it's quite cold there, minus 123 degrees Celsius at the poles. Nevertheless, during this time of year on Mars, you can still find not just ordinary snow, but 2 different types of snow. One is water-based, and the other is dry, made of carbon dioxide. And of course, there are snowflakes on Mars, and they have quite an unusual shape. What do water ice snowflakes on Earth look like? They are hexagonal because snowflakes are a crystalline structure. The asymmetry of such structures is hexagonal, meaning 6-sided. But on Mars, snowflakes made of dry ice are cube-shaped, meaning they have 4-sided symmetry. Martian snowflakes are very small. They are hardly visible to the naked eye. Snow doesn't appear all over the surface of Mars, mostly at the poles, which are the coldest areas. And in most cases, snow accumulates on the slopes of highlands or in the craters of extinct volcanoes. However, in most cases, water snow doesn't even have time to reach the surface of Mars and turns into gas. It's all about the atmosphere. It's very thin. Since we're already talking about the atmosphere of Mars, The MAVEN spacecraft is studying it to track how it has changed over different periods of time and why. And the reason why the atmosphere is becoming thinner and thinner is the solar wind. The planet gradually cooled down, and with that, the shielding effect of the global magnetic field also diminished. So what happens on Mars when spring comes? The process of melting Martian ice begins, and some rather interesting ice formations are created. In spring, geysers also start to erupt. Not only orbital probes can tell us about Mars, but also the rovers, which have been carrying out their missions for several years now. And we'll start with the nuclear-powered rover Perseverance. It is one of the newest Mars rovers, which landed on the surface of Mars on February 18, 2021. For a long time, Perseverance has been exploring the Jezero impact crater. The main goal of the rover's mission is to understand what changes occurred on the surface of Mars in the early periods of time, as well as to find traces of microbial organisms. Thanks to Perseverance, we have obtained samples of the Martian atmosphere and regolith, as well as a huge number of photographs of the terrain formations on the red planet. Their number reaches 166,000. Here are some of them. The spacecraft InSight. It survived the most powerful storms. But despite this, it continues to perform its mission reliably. The spacecraft recorded a massive Martian earthquake. Moreover, it turned out to be the strongest one we know of on Mars. Some of its tremors could still be felt even 10 hours after the earthquake. InSight also managed to detect it, even though the presumed epicenter of the earthquake is about 2,000 kilometers away from it. In general, it's worth mentioning that Mars has quite high seismic activity. During InSight's time there, several hundred series of tremors were recorded. The study of Martian earthquakes will continue since such phenomena help us learn more about the terrain of Mars. And finally, the Curiosity rover. It has been faithfully serving space science since 2012. Fresh data from it comes in frequently. It pays special attention to the clouds of Mars. For example, Curiosity managed to notice how, during sunset, rays of the sun shone through clouds that were higher than the others. These are truly unique shots. Apparently, these clouds are made of dry ice and carbon dioxide, while the other clouds are made of water ice. Because the crystals in the clouds change size over time, we can observe something similar to a rainbow. However, as the saying goes, it's not just about the clouds. Curiosity also found traces of lakes that might have once existed on Mars. The rover is also exploring Mount Sharp, which is located in Gale Crater. It is believed that there was once a lake in this crater. Water flowed into it from Martian rivers, but over time it dried up. At the moment, Curiosity is exploring the sulfate-bearing unit of Mount Sharp. Back in 2016, the rover also discovered a metallic meteorite there, which was mainly composed of iron and nickel. The unique feature of this object is that it was most likely previously melted. The meteorite was named Egg Rock because of its rounded shape and unusually smooth surface. Created. Sometimes it seems to us that we know everything about the planets of the solar system. However, in reality, this is just an illusion. There are so many mysteries and secrets around us, and Mars is no exception here. It still has a lot left to reveal to us, and perhaps we may never learn much about its past. However, researchers and spacecraft are not wasting any time and are doing everything possible to uncover the red planet's mysterious past. The news about the earthquake in Turkey and Syria spread around the world. The shocking footage of destroyed houses left no one unmoved. News about disasters like this doesn't appear often. However, you should know that earthquakes don't happen just 2 or 3 times, but hundreds of times every day. Most earthquakes are so minor that people simply don't feel them. Unfortunately, sometimes there are tremors of enormous magnitude with tragic consequences. For example, the earthquake in Turkey had a magnitude of 7.8, resulting in tens of thousands of deaths. We definitely should learn more about such a destructive phenomenon. Why do earthquakes happen at all? Why are some weak and others strong? Is it possible to know in advance where an earthquake will occur? And why do vibrations, also known as microseisms, occur inside the Earth every 26 seconds? First, we need to understand what an earthquake is. These are tremors in the Earth's crust caused by periodic movements of rock masses deep within the Earth. This is largely facilitated by seismic waves. Earthquakes can be completely different. They can make the chandelier in your room shake a little, or they can wipe entire cities off the face of the Earth. Such phenomena can manifest not only as periodic shaking, but also as ground shifts. Earthquakes can also trigger tsunamis if the epicenter of the disaster is located in the depths of the sea. And that's not all. Volcanic eruptions can also be triggered by underground tremors, or even landslides. As you can see, earthquakes carry a destructive force. However, how is it that in some areas, strong earthquakes have occurred several times throughout history, while in others, they have never happened at all? Where are underground tremors most commonly observed? The Earth's structure consists of the crust, the mantle, the inner core, and the outer core. The crust is the solid layer of the Earth. At the same time, it is not a single solid shell, but rather separate blocks called lithospheric plates. The position of these plates is not static. They move and periodically overlap each other. As a result, a large number of cracks and faults appear. Some part of the lithospheric plate stops due to collisions with another, while another part continues moving. In areas where the fault boundaries are located, earthquakes most often occur. At a certain point, the stress caused by the internal differentiation of substances becomes greater than the force of friction. More and more cracks appear on the surface, and a huge amount of energy bursts out, which directly triggers the earthquake. There are different types of faults on the Earth's surface. The movements of the Earth's crust can be both horizontal and vertical. When the ground rises above the place where the Earth's crust has diverged, the fault is called a reverse fault. There are also inclined faults when they are not completely vertical or horizontal, but at an angle. It's important to remember that human activity can also trigger underground tremors. For example, in places where there are mines where oil and gas are extracted, geological activity is more intense. Since water, especially in large quantities, erodes and weakens rocks, reservoirs can also increase the chance of an earthquake. When it comes to earthquakes, the prefix seis is often used. A seismograph is used to record underground tremors. The recording of vibrations is called a seismogram. A seismograph consists of 2 parts. The first part is a relatively heavy weight on a spring, or in some cases on a wire. The second part is a special pin that is attached to the weight. These 2 parts remain stationary during oscillations, which allows the pin to draw waves of different amplitudes on the paper. This is called a seismogram. What factors determine the strength of an earthquake? The main factors are how deep the fault in the Earth's crust is, and how the lithospheric plates have shifted. At the epicenter of an earthquake, the depth of the fault ranges from 10 to 30 kilometers. In some cases, it can be even greater. An important parameter is the magnitude, which helps determine the amplitude of the vibrations. The magnitude scale ranges from 0 to 9. An increase of 1 point means an increase in energy by about 30 times. The intensity of the tremors can be determined using a 12-point scale. The location of an earthquake can be determined with the help of so-called P and S waves. The tremors from these waves occur differently because the speed of the P wave is higher than the speed of the S wave. Accordingly, this helps determine where the earthquake itself is happening. And the P waves, since they have a higher speed, cause the tremors first, and then the S waves come into play. But how exactly does this help determine the place where the earthquake is happening? The thing is, if the epicenter is close to a certain area, the time interval between the P and S waves is minimal. Often it's practically unnoticeable. But if the area is farther away, then the interval between these waves is greater. To determine the exact epicenter of an earthquake, you can use the triangulation method. For that, we'll need 3 seismographs. If we take a map and draw a circle around the location of each seismograph, the radius of each circle shows how far the device is from the earthquake. The point where all 3 circles intersect can be considered the epicenter of the disaster. All right, that's clear. However, one question still remains, and it's probably the one you're most concerned about. But can we calculate when an earthquake will happen? We hate to disappoint you, but no. Of course, scientists have been looking for ways to make this possible. However, they have not succeeded. An earthquake occurs in a specific place due to a combination of different factors, which also determine the severity of the consequences. The larger the ruptures in the Earth's crust, the greater the risk of destruction to important infrastructure such as power plants, dams, reservoirs, and more. Earthquakes can trigger volcanic eruptions, powerful tsunamis and landslides, and sometimes even forest fires. Remember at the beginning of the video we mentioned the vibrations that are detected every 26 seconds. We think it's time to tell you what that is. The tremors were first noticed by Jack Oliver in the 1960s. This phenomenon was called the pulse of the Earth. Oliver studied the data for a long time and with great effort. And as a result, he determined that the oscillations usually had a period of between 20 and 28 seconds. And these vibrations were actually acoustic waves. Eventually, the scientists concluded the vibration center was in the South Atlantic. However, the exact location was determined sometime later when the appropriate technologies became available. It turned out that the center of the vibration was Bona Bay, Oliver, located in the Gulf of Guinea. But why does such a phenomenon as the Earth's pulse exist at all? Jack Oliver himself suggested that the cause could be either magmatic activity or the movement of waves. Several decades later, as more data became available, the location of the vibration epicenter was specified. It was still in the Gulf of Guinea. This led to a new theory about the nature of the pulse of pulses. It may have formed due to the specific location of the continental shelf. There was also an opposing theory, according to which the volcanic activity on the island of São Tomé was to blame. Be that as it may, all the theories come down to the fact that the Gulf of Guinea is a unique area. On our channel, we talk a lot about the mysteries of space. However, even on Earth, there are many things that are not fully studied. And an example of this is underground vibrations and tremors. We know for sure that we are absolutely defenseless against the destructive power of our planet. Perhaps someday it will seem to us that we have subdued the forces of nature, but that will be nothing more than an illusion. And what do you think? In which direction will earthquake research go next? And will scientists ever be able to predict future earthquakes? Subtitle.